This video will discuss MGSE8 EE4, add and subtract, multiply and divide numbers expressed in scientific notation, including problems where both decimal and scientific notation are used.
Each time the exponent increases by 1, there's a 0 added. So if it's 10 cubed, then it'd be 3 zeros after the 1.
Okay, all right, great. What if we were to only focus on that digit of 1? So say, for example, let's start with 10 to the first. What number do you have as equivalent to 10 to the first?
10.
10. And then when we go to 10 squared, what happens to that digit of 1?
It goes
up a place.
It goes up a place. Wonderful. So it starts off in the tens place with 10 to the first, and then when we go to 10 squared, it moves to the hundreds place. Wonderful. What about as we go from 10 squared to 10 cubed?
It goes
down a place. Oh wait, 10 squared.
It goes to the thousands.
It goes to the thousands. It's still moving, as you say, up a place. So it's moving to the left on our place value chart, right? In 5th grade, students learn to explain patterns in the number of zeros of the product when multiplying a number by a power of 10, and explain patterns in the placement of the decimal point when a decimal is multiplied or divided by a power of 10, as well as use whole number exponents to denote powers of 10. In 6th grade, students learn to write and evaluate expressions involving whole number exponents and apply properties of operations to generate equivalent expressions. In 8th grade, students express and use numbers in scientific notation. Numbers in scientific notation are added, subtracted, multiplied, and divided. Students interpret the relative size of numbers in scientific notation generated with or without technology. This serves as one of the foundations for the quantity standards in high school, where students will reason quantitatively and use units of measure as a way to understand and solve problems. Students may learn how to multiply by 10, by 100, and by 1,000 by simply adding the appropriate number of zeros. Without having a solid understanding of powers of 10, students will quickly develop a misconception when working with scientific notation. One misconception students develop is that the exponent tells the number of zeros to add onto the number.
Enter 45 followed by a string of zeros. What happens when you press enter?
It changes to 4.5 times 10 to the square root of how many zeros you put in.
So you think that exponent tells you how many zeros you put in?
Yes. Yeah.
Address this misconception explicitly in discussion. Ask questions such as, why are there 14 zeros and not 15? Is there a relationship between the exponent and the number of zeros? You want students to conclude the relationship depends on how many non-zero digits are in the number. Take a look at this image. How do some of the elementary concepts pictured apply to 8th grade? Rather than focusing on the procedural aspects of this standard, spend time developing a deep understanding of the number sense involved in operating with very large and very small numbers. Avoid language such as the decimal point moves or adding zeros. Instead, focus on the shifting of the digits as the leading digit moves to the right or the left as the numbers are switched between standard form and scientific notation. Using base 10 blocks to model addition and subtraction of scientific notation will help to drive a discussion of the relative size of friendly very large and very small numbers. If you have them available, allow students to work in pairs or small groups with base 10 blocks. Virtual manipulatives are a good replacement if the concrete materials are unavailable. Building upon the work with base 10 blocks, an activity such as this will help to drive a discussion of relative size of friendly, very large, and very small numbers. Add 2 times 10 to the third plus 4 times 10 to the third. In this simplistic example, students will determine the types of blocks or powers of 10 remain the same, but the block or coefficients are added together. In a more complex example, such as 1 times 10 to the third minus 2 times 10 to the second, you should draw students' attention to the difference in the powers of 10. To remove 2 flats, the cube should be exchanged for 10 flats. The expression 1 times 10 to the third is rewritten as 10 times 10 to the second. Now we can remove the 2 flats, resulting in 8 times 10 to the second. In this clip, you'll see students working on the Exploring Patterns of 10 Frameworks task. This task uses numeric patterns to discover the rules as they select various values for the exponents as they go through the 4 operations. Students are encouraged to use the calculator to compute to keep the focus on discovering the patterns, which will lead to the rules. Because students should be comfortable working with numbers in both forms, you will want to encourage them to rewrite numbers written in standard form to scientific notation to help notice any pattern. Let's start by writing it with the 4 in the ones place, with the 4 digits shifting to the ones place. What would that look like?
The 4 shifting to the ones place?
And what would come after the decimal point? What do you think? And what'd you come up with?
4.52 times 4 to the power of 4. I mean 10 to the power
Wonderful.
of 4.
And let's see if that checks with the understanding that you said before. So if 4 was in the ones place, how many digits do we have behind it? 1, 2, 3, and 4. As students begin to delve in the problem-solving portion of this standard, they will often interpret the operations within real-world contexts. In the task Giant Burgers, from the Unit 2 Exponents and Equations Georgia Department of Education Math Frameworks, students should conclude the use of multiplication is needed to determine the number of people who eat at Giant Burger each day. To determine the percentage of Americans who eat at Giant Burger, students may choose to divide 2 times 10 to the 7th by 3 times 10 to the 8th.
You guys got to do 20 million divided by 300 million. It'll give you the decimal 0.76667.
Oh my gosh.
And then it'll if you round it, it'll be 6.6%.
Which turns it to 7, which makes it true.
Oh, I see now. I get it.
As you look at this example from a free resource developed by a team from Illustrative Mathematics, consider what operations students would need to use to determine which of these products have more storage, faster speed, and more memory. For each, they will have to determine how many times more the product has. Take some time to work through the task. More information on this task and others are available through the free resource link for the Illustrative Mathematics Open Resources found under this video.